This video introduces VCE Algorithmics students to recursion. Recursive algorithms use recursion, a method of solving problems by breaking them down into smaller problems and calling the same function within itself to solve those smaller problems. It is not a design pattern, but is often related to divide and conquer. We'll explore some basic terminology using a simple recursive function to find the factorial of a number. The idea is we start with a large input. The function is called itself again on a slightly smaller input and again until we get down to a base case, which is passed back up through the call stack. We'll see how this works and we'll explore some terminology using a simple recursive function to find the factorial of a number. Recall that, for example, 10 factorial, written 10 exclamation mark, is 10 times 9 times 8 all the way down to 1. Now, a non-recursive approach to finding 10 factorial, an iterative approach, is to start at 1 and work our way up to 10. And this is how our function might look. So this function does not call itself. We'll have a quick step through. We start with I equals 1, result equals 1, and we've called this with n equals 5. And we step through this, so we do result equals result times 1, and then we increment I. 1 times 2 is 2, increment I. 2 times 3 is 6, increment I. 6 times 4 is 24, increment I. Now let's just be careful on the condition here. We've just done I equals I plus 1. I is still less than or equal to n, so we are going to do result equals 5 times result, which is 120, which is the result we know we should get for 5 factorial. I equals I plus 1, and now we return the result. I thought I'd show you this so we can compare this to a recursive version. So when we call factorial 5, this function will call 5 times factorial of 4. And the factorial of 4 will call 4 times the factorial of 3, which calls 3 times the factorial of 2, which calls 2 times the factorial of 1. And when we call factorial of 1, this is what we call the base case, which just returns 1. And now look at how that's returned back up the call stack. Factorial of 1 was 1, so we return 2 times 1. That goes into the factorial of 3 call, so that's 3 times 2 times 1. We end up with 4 times 3 times 2 times 1, 5 times 4 times 3 times 2 times 1, which is what we were expecting. And we've highlighted here the base case, which is the bit at the bottom which does not call the function again. Note then how the function calls itself and it reduces the input towards the base case. If we didn't do that, the function would just call itself forever. This is what we call a tail recursive function, because the last line of the algorithm is the recursive call. This has some compiler-related advantages, not something we need to worry about too much for VCE Algo. Now when we make a recursive call, it is placed on the call stack. So we call factorial of 5, which then calls factorial of 4, which calls factorial of 3, factorial of 2, which calls factorial of 1. Factorial of 1 was the base case, so that gets popped from the call stack, which lets us then solve and pop factorial of 2, pop 3, pop 4, and eventually we pop 5, which solves our problem. So you can see how the returning values help us to unwind the call stack to solve our original problem. We'll look at some other examples. I found when solving these, it's good to take concrete examples rather than try to go straight into general definitions. Another classic example is the Fibonacci sequence. Recall that each term is made up of the sum of the 2 preceding terms, with the first 2 terms equaling 1. Sometimes you'll see the 0th term as 1. Either seems to be acceptable in algorithmics exams. Again, we'll start with this concrete case. So let's say we were trying to find the 6th Fibonacci number recursively. We would start at the top and work down. So the 6th is the 5th plus the 4th. We can see here how the 5th is the 4th plus the 3rd, and the 4th is the 3rd plus the 2nd. And we keep going down. And you can see how one of the base cases is the second number. So when we call fib of either 2 or 1, we just return 1. Otherwise, we keep going. We get a whole bunch of 1s on this line. And finally, we end up with a whole bunch of 1s. And these would, again, get unwound back up the call stack. The code for this is actually quite logical. So we start with our base case. Well, if n is less than or equal to 1, we return 1. So that's fib of 1 or 0 in this case. If you said n is less than or equal to 2, that would also be fine. Otherwise, we just return the sum of the previous two terms. Note that this is a horribly inefficient way to find Fibonacci numbers. We end up calling the same function multiple times. In Unit 4, we'll look at dynamic programming to make this better, though in this case, it's probably better just to use iteration, starting from the first two terms and working your way up to the one that you want. However, the nice thing with recursion here is it does represent how we think about Fibonacci numbers, and the algorithm itself is quite simple. The next example we will take is to see if a given string is a palindrome. That is to say, it reads the same forwards and backwards. Now is a good time to pause the video and at least think about how you might do this for yourself, maybe even have a go at writing the algorithm. Note that your algorithm must be recursive, so if you write an iterative algorithm when you're asked for a recursive one, you should expect close to 0 marks. I've given some examples here, which hopefully you can see as we do them, how they'll test a couple of different cases. Again, we're going to work from large to small. So let's think about how we deal with TacoCat. We check the first and the last letters. We say, well, they're okay. Let's work our way in. And we call the same algorithm with the string with the T's removed. We do the same thing with the A's removed, and then with the C's removed. And this shows us our base case, which is where we have just one letter. This will return true, and that value of true needs to get passed back up the call stack to return true for TacoCat. Now the next example, where we have Anna, our base case could also occur where the string has a length of 0. So our base case is going to happen where the length of the string is either 0 or 1. If we hit that base case, the value of true gets returned back up the call stack. So I've written this in very human pseudocode. If the first and the last letter of the text are the same, we remove those and we return PAL all the way up. Now we need our base case, which is if the length of the text is less than or equal to 1. We also need to account for the situation where the first and last letters of the string are not the same. So we return false if that initial if statement doesn't make the recursive call. Let's have a look at how this works. When we call PAL on Anna, it calls PAL of NN since A is the same as A, which calls PAL on an empty string, which returns true back up the call stack. We get true overall. When we call PAL of Harry, this just returns false straight away. And when we call PAL of Trot, this calls PAL of RO, because the T and T were the same, but then this returns false, which returns false back up the line. The final case we consider is a permutation generator. This is a particularly hard task to get your head around, so I start again by considering concrete examples. With the example of ABC, I've just generated the permutations by hand, and you can see how the pattern works. I start by considering A as my first letter, and all the possible options with A as the first letter, then B as the first letter, then C as the first letter. To build this up, I'm going to need to maintain a list of combinations I've made so far. The lists on the right give some idea of this. First, we consider all possible letters for the first item next to a list of all the letters that remain. Next, you can see for the first example, where A was the first letter, I consider all possibilities for the second letter, so AB, AC, and AD. And then I've just expanded one of the next levels down here. For the third letter, it can either be C or D, with D and C remaining respectively. Our base case in this case is going to be when there are no more elements in that right-hand list, which is to say we've used up all of our available letters. Now let's put this into code. We need the solutions so far as the current parameter and the elements as the items we are going to permute. So our initial call will need to include that empty list. First, we'll consider our base case, which is if there are no more elements to permutate, we just return current. What's particularly hard about this one is that we are making multiple recursive calls for each recursive call. So we need to set up a list called result, which is an empty list here, And then for each item in the elements, we're going to consider that as the next item to be added to result. So we call perms with that next item added to result, and the elements, the list of elements without that item, and we add that to the result, and then we return that result back up the chain. Now, it's hard to believe that such a small amount of code can solve this problem, but I've included the Python here, which is pretty close in structure to the code we've got there. It's not perfect due to the way it embeds the lists within each other, but it's pretty good and certainly fine for VCE Algorithmics. So, in summary, we've seen how recursion is used to break problems down into smaller problems. We've seen how the functions call themselves, and we've seen how each function call must make progress towards that base case. Why do we use recursion? Well, it is a natural fit for things like trees or state diagrams where we search down branches. It's adaptable to backtracking, which is a design pattern you'll see in Unit 4, but you may read about as we go along. That's where we stop a recursive call when we realize it's not going to take us to a solution we're interested in. Recursion is also simpler and more readable, particularly when we're following a divide and conquer approach, which you may or may not know about right now. Sometimes that decision is quite easy to make, sometimes it's 50-50, for example with Fibonacci, and sometimes it's not the best. The downsides of recursion: it is conceptually challenging. I think that's a bit of a naff downside, just get better at coding. Deep recursion will eventually cause stack overflow. So if you're dealing with huge inputs, then recursion may not be appropriate. And sometimes it's not a logical fit at all. Now, there are heaps of examples of recursion to try on the internet. The more you practice, the better at this you'll get.